We next talk briefly about Newton's law of universal gravitation. Newton's law of universal gravitation says that if you have a mass 1 and a mass 2, and these are officially point masses, although this also applies to spherically symmetric masses that are separated by enough distance that they don't interpenetrate one another. In this situation, the force of attraction between the two objects is G, which is a universal constant, the universal gravitational constant, multiplied by the product of the two masses divided by the square of the separation of the two masses, or of the centers of the two masses if you got spherically symmetric masses. So force is then proportional to the product of the masses and inversely proportional to the square of their separation, and G is your proportionality constant. Now, a more rigorous law, F is negative G times M1 M2 over R squared multiplied by R over the magnitude of R. Now there's a little more, this has to get a little bit more specific. This just has the same expression for the force here. The R over the magnitude of R, and I say little r, the R over the magnitude of R is just a unit vector in the direction of R. And the force is going to be, in this case, is going to be in the direction opposite R. R over magnitude of R is in the direction of R, so we put a negative out here. And we then multiply that unit vector by the negative and the magnitude of the force, and we get the vector force. This will become important later, so it's worth thinking about now. I'll also mention the magnitude of R is just little r, so you could represent this as an r cubed here and an r vector over here. But if you do that, you lose the whole idea of magnitude times unit vector. It's more efficient to write it that way, but you lose the idea of what's going on. So you have to make sure you understand the idea before you go complicating the expression or simplifying it, whichever way you want to look at it. Okay, well, we want to apply this law of universal gravitation to a satellite in a circular orbit at velocity v around a planet. So we'll let M1 be the mass of the planet and M2 the mass of the satellite, and we have the r vector from the center of the planet out to the satellite. Now the condition for a circular orbit, if you're moving in a circle of radius r, then you have to have centripetal acceleration to keep yourself in the circle. If you don't have that centripetal acceleration, then you're not going to stay in the circle. It's just part of moving around a circle at constant velocity, or actually at any velocity. But so for a circular orbit, you're going to have centripetal force as v squared over r. That means the centripetal force on this mass M2, well, is mass times acceleration. M2 times your centripetal accelerations, M2 times v squared over r. So you have a centripetal force that keeps turning this mass toward the center of the planet as the mass tries to fly off in a straight direction. Now, where does the centripetal force to hold the planet in a circle come from? It comes from the force of gravity. It comes from the gravitational attraction governed by this law. So what do we have? We have M2 times v squared over r equals, this being the centripetal force, equals the force exerted by gravity on the mass M2. Now this is an expression we can easily solve for v, but this is where class ended, so this will end the class review, and I'm going to extend it a little bit in the next clip.